So, so when you say when you're taking it, when you're doing an overtaking, then distance you also come in picture. Um, yes, in one sense, you look at a safe gap. So when you're doing an overtaking, doing a lane change, then that moment of time you look at whether we have a safe gap or not, and that safe gap is generally, you know, from you as a perspective, it is yes, is in terms of meters, how much should be the safe gap, but based on speed and headway and spacing, all of them are related. We talked about the concept of headway so that we can estimate the flow values. Headway and flow are related to each other. So time gap between two ones can be converted into the flow. Then time to collision and all those things is when you talk about safety things, it is always in terms of time. At what speed you're moving and how much is the time gap between them. So these parameters are actually important to understand different aspects. So spacing is important when you want to do a lane change. You want to look at the space gap between the nearby lane. So at that time, yes, lane change, that spacing parameter makes sense. But how much is the spacing, the lead spacing and the drag spacing means if I'm here, I want to make a lane change. I have one vehicle there, one vehicle here. So with respect to me, how much is the lead gap? How much is the lag one? And then you make a lane change. So then spacing becomes important. Yeah.
So, overtaking side distance,
Yeah.
where all the headway, time, gap, all is measured. So, if it is less than overtaking side distance, there is a formula because it's like a three components. When you are making an overtake, first you need to see like if it is like an undivided road. First you will see whether there is some traffic is there from the other side. Then you'll make a judgment to increase your speed because if you are going to make an overtake, you have to have a higher speed than the vehicle you have to overtake. Then you have to maintain that speed, then you will increase your speed and at some point of time you merge to the other lane. So this entire operation actually needs certain time and certain distance is needed. So that's how overtaking side distance is calculated. If it is not there, then there's no overtaking zone usually come in between. So it is less than that because in curves and all, it is not possible to have that kind of distance, that kind of vision because you are not able to see. Then we restrict that we'll say that this zone is not
Yeah.
for overtaking.
Yeah, that's good. In fact, headway is equal to speed times spacing, right? So spacing is equal to speed times headway. All of them are interrelated to each other with the speed in between. So things like whether I give you headway or I give you spacing, they are like, and I give you speed, you can figure out one value from another. It all depends on the application you're looking at. So for the lane change, you look at the spacing aspect. For the flow estimation, the headway is there. Yeah. Good question.
In like Chennai city, people are usually in weekend they go out and the Sunday night or Monday early morning, so heavy traffic while they approach to the city.
Yeah.
So here, what I was thinking like railway in India, as per Indian scenario, railway ticket booking, we can come to know there how much waiting is or how the trend is
Yeah.
there. From that, we can predict there will be any correlation
Yeah.
between this and on-road
Yeah.
traffic.
Yeah.
It's possible to predict what will happen next day based on the booking.
Booking of?
Railway tickets.
Oh, you're talking about the correlationship between the railway booking and the traffic or traffic on the road. But it will depend on, so railway booking, like basically how many people have booked to board on that day or alight on that day at that location. So yes, from that point of view, you can say how much demand is expected to go at that station on that specific time of the day or day of the week, or how much demand is expected. So that is something you can know. I mean, even like if you study the pattern of your station, you can get that value. But that demand might be coming from anywhere, spread out.
Yes.
So you can have somebody coming from north, south, east, west, and so it is. I mean, the amount of traffic on the road.
Inside the city, only the roads which are connecting from different cities to
So you're saying that the intercity connection, given that you have understanding of the amount of demand who have booked the rail ticket on that day, means that might have a correlation with the amount of traffic which is going from A to B. Like if, but then that has a correlation with the school holidays and other things. So you can easily predict that okay, during these time period of the year, I have high demand, high volume going from between cities. So that I think the correlation will be much higher with respect to the type of the day, school holidays, public holidays, any function activities, traffic will be that way. But given the flow value of a specific corridor or the traffic for a specific corridor, and you have a historical database, you can easily make a forecasting of what will happen easily. But I mean, traffic is quite repetitive. I mean, human behavior is quite repetitive in that sense. To a certain extent, you can forecast. It is expected that this time of the day, this time of the year, I will have high demand because of XYZ activities. Yeah. Mm-hmm. Any other questions? Where are your students? Master, I just think we can start. Okay, we can start now because I think we have plenty to cover. Yeah. So those who are not able to join, I mean, they can ask questions later on. Yeah. So it's only 9:10. Is okay, or we have to wait for 5 more minutes? Start. Yeah. Now, in the last lecture, we were talking about Bluetooth loops. We have talked about vehicle trajectories also, and somebody asked a question that if we have data from all these sources, can you fuse them? Can you actually bring them together to have better understanding? Like for example, loops. We know that loops can provide us the traffic volume, the flow. Only I think loop is one of the important sources of data which tells you how much traffic is on that road in terms of the number of vehicles. Bluetooth can give you travel time. It can tell you how much is the travel time from A to B, but from a sample only. It will not tell you how many vehicles were there. It can give you, let's say you have a sample from a 5%, 10%, but you don't know what that percentage is. But loops is going to give you the volume. But both of them alone cannot give you density. Loop can give you an estimate of the density quite well on the motorways. Given that you have a speed, you have a flow, you can get a density estimate. But on the arterials where you have signalized intersections, traffic is quite different. Like traffic has to stop at the intersection, queue forms, and the traffic is coming from all the sources. Loop is only just one focus eye, depending on where you have installed it. It can be a stop line, it can be upstream, it can be advanced detector, anywhere. You only have that information, and you cannot just correlate it straight away to the density. So we can fuse them together. We can fuse these two information together to get some density estimate. And also we can fuse them together to fill the gaps. In fact, we discussed that there are instances when the sample size is not strong enough for you to have a confidence in your average travel time estimation from the Bluetooth. There are instances when you do not have a data set from one of the sensors and you do not get the travel time. So when those things are there, you can always fill the gap by actually integrating the two together. One of the ways by which you can do this is basically a model called CubeRide, which is cumulative plot and probe integration for travel time estimation. We use the word probe because probe is like, think of probe as any source which is giving you a travel time value for an individual vehicle. It can be a Bluetooth based travel time, it can be a GPS coordinates based individual vehicle travel time, any source. That's what we are calling as a probe. It works on a very simple concept, cumulative plots. You all must have studied about the cumulative plots. Imagine you have a counter here. At time t1 you count the first vehicle, time t2 you count the second vehicle. So as the vehicle is approaching, and just keep on cumulatively adding that. That's a cumulative plot. Means it's a cumulative counting of the vehicles as they are flowing from a specific location. You have a time when you put it as a 0 starting point, but you get like this. This is very strong plot because if I look at this, between time t and t plus delta t, just by looking at the plot, I can tell how many vehicles have arrived in the time period. So let's say this is 20, this is 10, then 10 vehicles have arrived within that time interval. Slope of this tells you the rate at which the vehicle is arriving. So you can get the cumulative plots, right? And you know that loops are the counters, they are basically counting the vehicles. You can get the cumulative plot from the loops. Here I've used them as individual vehicles because imagine you have a pulse type of information, but loops generally what you get or what you extract from the system generally can be is in terms of aggregation time interval. It might be 20-second aggregated value or 1 minute aggregated value. So you might say in 1 minute you have 30 vehicles arrived. So it will go from 1 to 30 in just 1 minute, right? Now imagine you have loops at two locations A and B. Let's call it downstream. The traffic is flowing like this at downstream and upstream. At upstream, you can have an upstream counter. We call it upstream cumulative plot. Let's call it UT as a function. Downstream, you have another cumulative plot. We call it DT. Right? Imagine that road was empty in the beginning. Then, at time t, what does this difference tells you? At any given time, the vertical distance between the two plots, what does that represents? Sorry? Sorry? But then let's say there's only one lane. So you have a plot here, you have a plot there. Hmm. Hmm. Yeah. No, because imagine like this. This at until time t at upstream, this is the number of vehicles you have observed. Let's say this is 500, for example. Then at time t, at the same time t, maybe you have observed maybe 400 vehicles at downstream. So that this gap, what does it tells you? Density or the number of vehicles which are, because 500 have entered, 400 have left, the gap is 100, so 100 must be somewhere from here to there, that's all, right? It is a number of vehicles between these two locations. Under the assumption that the counter has started at the time when there was nobody inside. Or you have basically have an initial starting point considering the number of vehicles which were there. Right, that's one of the important assumptions we are making here. For any vehicle I, because these are the vehicles, right? Let's say this is the ith number of the vehicle which has arrived. Single lane, there is no way to overtake. Whatever comes first has to exit first. Whatever comes last has to exit last. So first in, first out is there. So first in, first out. Please keep in mind that's so means I have a vehicle ith number. What does this time gap? Because now if I look at the as the horizontal distance, it is along the time axis. Vertical distance is along the number of vehicle axis, right? So what does this represents? The horizontal distance, travel time. So it says that this vehicle I was at upstream at time t1, was at downstream at time t2. That is the travel time. So by looking at the cumulative plots, which is we also call the input-output plots, I can easily get the number of vehicles between the two locations. I can easily get the density between the travel time. So basically, the density will be this one ut minus dt divided by the length of the road, right? So that will be density. If I want to write it, it will be simply density will be. Oh, sorry. This density will be u at time t minus d at time t divided by the length of the road, which is that is the length, right? And the travel time will be simply whatever is this time 1 and time here. So this time will be d inverse of I. This time will be the u inverse of I, if that's a function I'm talking about. Travel time will be simply d inverse for the ith minus u inverse of the ith, right? It is this time minus that time, right? So you can know that easily. I mean, because I've assumed u as a function, right? So any time t, you get a counter, you get a u. So I'm taking an inverse function of that, right? Now, um, now for any given time interval here, imagine this is 5 minutes. Lambda is 5 minutes. So at time t, maybe 2.5 minutes before, 2.5 minutes after. So I'm looking at now a specific time interval. For this time interval, the number of vehicles arrived is that many, right? Now that's the time interval. So at this time, that many number of vehicles have arrived upstream. Initially, that many number of vehicles have arrived at upstream. So that gap from here to here, the vertical gap, is the number of vehicles which have just arrived at upstream. You're fine with that? All right. Let's keep moving. So that is the number of vehicles which have arrived upstream. Now, what is the total? How will you represent the total travel time for all these vehicles which have arrived upstream? We know the vertical gap was one vehicle travel time. What is the total travel time? All of them. So you start accumulating all of them one by one, right? If you start doing it, it turns out to be that area. That's the way, right? You start accumulating it. The interesting thing here is, in the previous case I said that was the travel time under first in, first out. Now, generally traffic will never be first in, first out except for the case when you have a single lane. But if you have multiple lanes, there will be overtaking happening. So it can happen that this specific vehicle, maybe this specific vehicle, might have arrived in this order, might have left there. So its travel time might be quite different. So interesting thing is, if I let's say a specific vehicle which has arrived here might go at that time. Other vehicle might have arrived here but might have a shorter travel time based on the way they have done it. So what happens is that if you have all the vehicles which have arrived upstream are also departing at downstream within that time interval, if they represent the same vehicle, then that overestimation and underestimation of travel time cancels out, and this area will still represent the average travel time. Because imagine here, there's one vehicle which has a travel time of maybe 50 seconds, but it is represented here as 40 seconds. And that extra 10 seconds might have been, I would say, overestimated for the other vehicle. So when you keep on adding all the travel times, the area will still be the same, provided all these vehicles are the same as the one which have left there, right? So there will be an error because it will never happen that way. There are some vehicles from here going there also, so there will be some error. But if your estimation interval is large enough, you should not have that much error there. So this still holds even if the first in, first out is not there. Or it has to do with the number of lanes. If you have one lane, yes, it has to be first in, first out. You have two lanes, there are chances people will overtake each other. No, the error will be there. If there are two lanes, there will be an error. But let's say it's like this. Imagine we are 4 people here. I leave first, and it took me 30 seconds to reach there, and I was the first one. From at the upstream, I was the first one. But then you left, and it took you maybe 20 seconds to reach there. So at downstream, you are the first one to leave. Upstream, I was the first one to. So in the counter, upstream, I am the one, but the downstream counter, you were the one. But at upstream, you were the second one to come, and at downstream, I was the second one to come. So but this is the travel time given to me. So your travel time is given to me, and my travel time is given to you. So when you add the two travel times together, it's still the same travel time for us. It makes sense now? So provided, that's what I'm saying, if the same number of vehicles have left upstream and downstream, then it will balance out. Ultimately, it is giving you travel time, right, based on the counters, but it will have those errors. Individual vehicle travel time. That's why when I was talking about this one, I said single lane, I said first in, first out. So it is exactly the same vehicle. But if there are two lanes, there will be overtaking happening. So that's a good thing. Average travel time can be estimated easily by the cumulative plots. This is just expressing same thing in equation form. You know the travel time, you know the length, you know the average speed also, right? Which is the total distance traveled over total time taken. That's not a big thing. Don't worry about these equations. This is simply what I said. They're just citing that way. It just sounds scary when you write in this functional forms. Now, the vertical distance we said was the density, right? Or the number of vehicles from upstream to downstream divided by the length is the density. If I look here, what is the total density in this region? So from doing the time interval delta or lambda, sorry, it should be again summing all the vertical ones. So that area should be the density, total density in that time period. Yeah. So an average density should be, you just divide that by time interval. That is an average estimate of density in that time interval. Which is in this particular case, because you have an upstream curve, downstream curve. If you subtract these two curves, just take an integral from T2 to T1, you will get that. Yeah. In the previous case, it was the horizontal area, so you can't take an integral. Here it is the vertical area, you can take the integral. Are you fine with this? So technically, if you have the loops, you can find loops at point A, point B, you can get the things quite easily. But it's not, the real world is not that beautiful. Let's have a look. It's a simple intersection along one of the roads. Intersection here. Because at this intersection you have a stop and go running condition. Vehicle stops during the green time, during the red time, then flush during the green time, right? And if I give you an aggregation value of, let's say, every 1 minute, you cannot assume that the cumulative plot will have a straight line in that 1 minute. It should have some shape. Other important thing here is, you have an entry flow. This is, let's say, your study link for which you want to estimate the density. You have different types of exits happening. But more important is, you might have some parking on the road. You might have some slip also happening. So you might have entry and exit. So flow is not conserved. In the initial example, I show the flow is conserved. So and you have different turning moments also, which is contributing to different, I would say, density values or different Q lengths. And other important thing which we should never ever forget, detector has its own counting error. Plus minus 5% is easy counting that you will get an error into it. So if you just keep on accumulating with the detectors, the errors will have an impact. Just to give you an example, simple example, you have upstream, downstream, there is a side street, traffic is always leaving the side street in the middle. We call this a mid-link sink. So you observe 300 upstream, but only 270 has left downstream because 30 have been lost. So in this particular case, if you just continue drawing your cumulative plot at upstream and downstream, after a while they have drifted. You call them as a drifting issue. They just keep on drifting. On the other hand, if you have a addition from in between, they will just cross each other out, which is totally not going to make sense. That you have less number of arrival, more number of departure. So technically, in this simple example, you can see that because of drifting, the error keeps on accumulating. Error keeps on growing exponentially. So it's almost useless to apply the input-output if you just use that alone. So although that technique in itself can give you density, can actually give you speed and all those things easily, but you can't do that. Yeah. So what can be done here? If I have another source of information like travel time from some source for few vehicles, I can think of doing something on the plot so that I can minimize this error. I can try, if they are trying to drift, I will try to bring them together after a while because I have some reference with me, and that's the whole concept behind it. So, any question on this so far? We also call this the input-output plots. You might have studied about this, or might read about this. Input-output plots is also another thing we call this one. Which error? Oh, this the detector error is, you can have a 5% counting error easily, plus minus 5%. So, but this error, because you are starting, let's say, at a specific time, the error keeps on accumulating. So it just keeps on accumulating, and it will, after a while, it will be totally out. Acceptable limit in terms of your travel time estimation, density estimation, it depends on your application. You might say I might have 5%, 10%, 20%. It is totally on your application at hand. But with this strategy, after a while, these things is totally useless. Even that while can be 15, 20 minutes or half an hour. You cannot use it at all, because you do not know what's happening.
So, something at the entry point where you want to and the exit point.
Yeah. Oh, then you 3, 4, you accumulate them. They should be on different lanes, right? So if I have 2 lanes, I should have 2 loops there, each for one of the lanes, and you have to accumulate them together. Because what you want is how many. So think them as a counters. It should be counting the number of vehicles moving there. We are only considering the counting here. Yeah, if you place something in between, that's good for you. That's good. But that is going to cost us. Yeah. But if you place ideally in this particular case, you can put a counter somewhere here, wherever there's an entry and exit. That's what you should be doing. Then you will have more confidence. Then you can use it actually. But you never have that. In fact, we have seen that for traffic signals. Let's say the loops can be at the stop line. So you have a stop line here, you can have a stop line loop there. So you know what proportion of traffic might be coming under certain assumption of turning proportions. Because every intersection will have a stop line loops. So the stop line, for example, the stop line here is an upstream for the downstream one. But you have to consider the turning proportions. But there is some traffic which might be turning left. So you have to take them off before you assign how many of them are going downstream.
A lot of them will be depending on
What
what is there, right?
is?
For example, if it says 10, then what happens if something is block this road? Go left around.
Yeah, that's fine. That's okay. That's good.
They can open it in the later part.
So you should know those. You should know those operational constraints. That should be known to you. Yeah. Like for example, you can have during the morning peak period, no left turn is allowed, and also evening peak period, no left turn is allowed. But during the normal time, it is allowed. That's fine. You will have that. That's okay. But you should know those constraints, that the time interval we are talking about. Yes, those are the initial knowledge you should have about the system. Yeah. So let's have a look now. Other thing I mentioned about to you earlier, that detection is going to give you, or the detector is going to give you an aggregate value for, let's say, 1 minute or 2 minutes for that specific intersection or loop, right? And you are assuming a uniform arrival. If you want to have a more better shape of this cumulative plot, you need to have a signal timings with you if you want to have more better shape. And that signal timings are during the red time and green time should known to you. During the red time, there should not be any flow. During the green time only, you should have the flow. So if you know the signal red time and green time, you can further modify this uniform flow rate or uniform detection cumulative plot for that detection interval into a shape where only the green is given, the flow, red is not given any flow. So you can have this one, which is very important because this point there is no flow happening, right? And if the signal is undersaturated, the vehicle leaving at this specific time should have the almost 3/4 travel time. Means imagine the last vehicle trying to enter exit the green and there's no queue left over at the end, should have the free flow travel time. So it is giving you additional information that there is that the gap between the loops, the horizontal gap at that time should be close to 3/4 travel time. So you are getting some more, I would say, hook points to adjust the cumulative plots. I call them as a virtual probes, only under saturated condition. For example, here flow should be 0, you know the proportion of the green which is, so this is the detection interval. Let's say in 1 minute you have observed, for example, 50 vehicles. So ND is 50 here, for example. Let's just for sake. Out of that 1 minute, 50% of the time there was a green, sorry, there was red. So I know there should not be any flow here. Maybe 40 seconds were here, 20 seconds were there. So you say 40% of my 50 vehicles should go here, other 20% should go. I mean, whatever percentage it comes out to be, you just allocate that way, and you can change the shape the way you are changing here. You can further change it for the arterial intersections. Does that make sense? Yeah. On it is. We're not doing any interpolation. We are just, see, if I say in 60 seconds you have observed 40 vehicles, right? So and before there was no vehicle, 60 seconds you have 40. So if you only know that, okay, from here to there you go a straight line like this when you draw the cumulative plot. Yes, but I know that during green time there should not be any flow. So I will say out of this 60 seconds, maybe 30 seconds was no flow. So I know that this 30 seconds, whenever I am drawing, I should not have any flow. There should not be any increment. The balance, I will do the increment. And that increment, I will just increase them based on what proportion of the green is there. Maybe 80% of my green is here, 20% of my green is there. So that increment, 80% increment I will do here, 20% increment I will do there, that's all. I mean, generally, if you have 5 minutes and you have signal timings, you just keep on doing that way, under assumption that your arrivals are uniform. You want to make it a bit more, the shape should take into account the kind of flow. Technically, it still has some errors. If you are approaching towards the end of the green, you might have a different flow rate compared to the start of the green, right? So you want, but you don't want to go to that much complexity. I'm just trying to simplify that process. So the concept here is very simple. You have upstream and you have a downstream plots with you, and you know that because of the error in the data set, these plots will have a, because of the drifting issue, they don't have a good, applicability alone. So you have a probe data set with you. Probe means a Bluetooth travel time or some travel time value. A vehicle was at time T1 at upstream and T2 at downstream. So you have a TU and 3D as two vectors for individual vehicles. So each element is one vehicle, for example. So for example, these are the two probes. So the time, and this was the time when the vehicle first one is upstream and then it was downstream and so on. I can basically, because I know my time, based on the time, I can hook them to one of the cumulative plots. I am fixing it to the downstream in this case because I have a downstream loop detector. I have more confidence in what I am observing at downstream. So if you fix them here, you have the hook points at upstream. So your upstream should pass through this one, but you can see that because of the non-first in first out issue, if you just try to pass them, you will have a zigzag manner. And cumulative plot should always be increasing with respect to time. It should not go back. I hope you can see the, like for example, ideally this guy should be here and this guy should be there, right? So the travel time for this guy should be that much. Travel time for, I should draw it here for, yeah. So this is an example which should tell you why there was an error. Like if you look here, if I look at the counter, this person, the second person, was first observed at upstream, but was second observed at downstream. First person was second observed upstream, but he might be driving fast. Was first observed downstream, right? So if you look here, if I would have drawn the cumulative plot for these, it should have been something like this. So that's the first one. That's the second one, and this should have been the cumulative plot for the downstream one. The second downstream would have been a cumulative plot like that. If I just use that one, right? You can see I am I'm for this one, I'm doing some error in my travel time. But I'm underestimating here, I'm overestimating here. And because these two vehicles are same at upstream, downstream, they will balance out each other. If I sum this travel time and sum that travel time, that is same as the actual travel time they would have taken. So now I hope you understand that when I said that even without the first in first out, if you're taking the area, they should balance each other out, as long as the vehicles at upstream are same as downstream. Yeah. Can I have some water, please? Yeah. It makes sense?
But in between, if something has to hold the critical.
Oh, that might have added. So that is a noise that which is there. You can't do much there. So what we will try to do is we try to get rid of that one. Oh, thank you. Yeah. And that is what we're trying to do, because this whole errors are because of that one. I mean, if there was no noise, you would have got this kind of plot. The one I've shown, that's the plot you would have got. Then it was perfect. Because somebody might have added in between, that's why you have these kind of issues. So now what we do is, the virtual probes which I was saying was at the end of the green time. But let's say if I know those points, I can readjust my cumulative plot so that it passes through those points. And I need an algorithm to do that, right? And once you have it, you have a redefined cumulative plot, and then you can use it for travel time and density estimation. So this was the whole overall concept. Let's see how do we redefine it. What algorithm? How do we make sure that, okay, this is how it passes? So the concept here is you can fix it to downstream, or you can fix it to upstream, depending on your confidence in the estimate of the cumulative plot or the application. You want to minimize the errors which are there, right? So let's say I'm fixing it to downstream. That's my downstream cumulative plot. I have fixed all my probes there. Obviously, in this space, I know that my actually redefined cumulative plot should pass through these hook points. So if they pass through this one, then any underestimation is compensated by the overestimation, underestimation compensated by overestimation, and that's how you can balance out things. I mean, you can see this quite easily how it looks like. I mean, when you plot it, you draw the lines, the diagonal is the one you are interested in. So I came up with a very simple algorithm for it, which is you have the list of your upstream and downstream data points. So this one is time upstream for the first one, time upstream for second one, time upstream for the fourth one, time upstream for the third one, right? You have the list of your upstream data points. Similarly, you have a list of your downstream data points. You have a list like this. What you can do is, if you sort your upstream in the order of time and hook it with and this sort downstream. So you sort upstream independent of downstream. So sort two separate lists independent of each other, and you merge them together. The points that you're going to get here will be your points to pass. Naturally, they are the diagonal points. That's the algorithm. Very simple one. So 3U4 is now merged with TD3 as your probe, and you naturally get those dot points. Now you want to write a code to do it. You don't want to do it manually, right? Every time. So this is how you can do it. Just get your list of upstream, list of downstream, sort them. It will come that way. So once you have this, I can readjust my cumulative plots. So I might have a reference point. I have already identified my point to pass. What are the point to pass? This is a cumulative plot I have. So what can I do now? What should I do so that this plot passes here? So you have a hook point earlier, right? Where you have confidence. You want to pass this plot from here. What can you do? Shifting means you shift it like this. If I shift it like this, I am basically missing. I will also be, screwing up with my initial hook. It has to be hooked here, right? Sorry, adjust other data points. Yes. Mm-hmm.
Possible that point, right?
Mm-hmm.
You make the optimization on the count. You make the count.
So you are saying that just bring it like this.
Yeah.
You're here, just bring it like this. But if you bring it like this thing will also go that way, right? Yeah. So you can bring overall like this, or because that is the only reference point you have. After this, you do not know. Like that's the only point you need. So you will combine the two together. You will say from here to there, I will do the vertical scaling. So I know this is at one point. I will scale it up or scale down depending on how I will scale it. In this case, we are scaling down, bringing it to that part. Then the other part is vertical shifting. You just bring down as it is. Because that cumulative one that you have generated, you do not know whether there was an error or not. Here until point only you know that, right? So you do the vertical scaling and you do the vertical shifting. Once you get a new point to pass, then your previous point to pass should become your reference point. And you do the same thing again, vertical shifting and scaling. And you keep on moving like that. Does it make sense?
So that process vertical
Error in the sense? No, the cumulative plot is still continuous, right? It's still continuous. It's not changing. I mean, in between this one, we do not have any knowledge. So we can't do anything in between. The only knowledge we have is at those reference points, right? Yes, if this is after 15 minutes, any error in the 15 minutes, we had no information in the past. So that, but whatever shape we have observed when we had done the scaling, we have brought it down to the point where we have the confidence.
The reference point is already our Bluetooth. That's why the Bluetooth is right.
Yeah.
And by doing adjustment, we have reduced the error. Now with this new curve, what we want to do?
Oh, that we want to get the travel time and density. So this is what we are doing. I mean, basically, when I was talking about the cumulative plot in the beginning, at the end of the day, this is what you will do. Once you have upstream and downstream, you can use that to estimate density, or you can use it to estimate average travel time. But only when you have the confidence in these two. So what I'm doing all is, and I said that look, you don't have enough confidence because of all these errors, right? They might be drifting away. So you need some hook points to have the confidence. So now basically what you have done is, this is what you had, but with the hook points you have brought this blue line. And now you're going to use the blue line and the green line to estimate your density and travel time, not your initial red line and the green line. Yeah? Yes, let's have a look on that. So obviously, once we have done this work, we wanted to do some validation. Let's go for this validation. So what we did was, we know the Bluetooth travel time. We intentionally took some data out, right? And now I do not know the travel time at this point. I want to estimate the travel time. So we actually did that. This is around the coordination drive. I had a good Bluetooth travel time information. I was taking my Bluetooth data points out, as you can see here, and all those things. And we try to fill that gap by the integration of the Bluetooth that you had from the other points and the cumulative plots. So this portion, you do not have any Bluetooth. You had it before, you had it after. So you use that before after Bluetooth points and the loops for the whole time period to fill the gap. And this is what you got. So this is your travel time from the Bluetooth, assuming that was perfect in the beginning. This is the travel time that you estimate from Cuprite for the time periods when you assume there was no Bluetooth, and show some good correlation. This from the, so for travel time you can do that, right? So it is around 10% improvement. Cupid has 10% in the mean accuracy, 50% improvement in the, I mean, these are the values, don't worry about it. It shows some good result, right? It can be 10%, 15%, 20%, some value will be there. But when it comes to density, we do not know the real value of the density on the network. So I cannot do any validation from the real data set. So for this, I had to rely on simulation. So I went back to the previous simulation tool we have developed for integrating Bluetooth with the traffic simulation tool. We perform a simulation along the corridor, make our own corridor, get, so in simulation you can know everything. You know everything was happening. You put the loops wherever you want to put the loops, did some manipulation in terms of the way you define the density along the corridor based on your input output things, and we try to benchmark the density that you are getting from your simulation with the one that you get from the by applying the algorithm, and it shows some good estimates. As I tell you earlier also, the results are whatever they are, right? They will be just it can be, let's say, 90% accurate, can be 85% accurate, depending on whatever scenarios we have selected. But what is important here is this concept is working quite fine. It's giving you a good estimate. Even if it is less than 90% accurate, we are happy with that. For example, here, this is based on the Bluetooth penetration rate, the percentage of the Bluetooth you are selecting from your traffic. 1%, you get an accuracy of maybe mean accuracy of maybe 92%. And A5 means is the 5th percentile of the accuracy. It means that 95% of the time your accuracy was at least 80%, right? So which means that how much reliability you have in your system. I mean, I can have a mean accuracy of 80%, but that mean accuracy of 80% can lie between 60% to 98%. The reliability is very bad. But if I have a mean accuracy of 80% and that accuracy varies between 78 to 82, the reliability is good. So that's what you are looking at here, right? So this is when you're considering the mid-link sink and the mid-link source, means somebody is entering or somebody is leaving. So you consider two different scenarios. But at the end of the day, you can see that as the penetration rate is going to increase, more and more information you have from the travel time, hook points, more accuracy you are going to. So your question, if I only have a reference point, one hook point, one reference point, what can you say in between? So if you have 1%, you will have it quite far apart. So your errors are still higher. If you have 20%, you have more closer reference point, you have more accuracy. So it's quite naturally, as your penetration rate is going to increase, you will have more and more confidence in your estimation. But you don't have any other knowledge, any other information. So that's the best you can do at that time.
Starting off with the density curve initially only with the loops, right? Initially one calculate the density. Only the loop.
Yeah, so that's what so density value from the loops Q is equal to K times V works quite fine when you are on the expressway. So you have a loop here, traffic won't change dramatically other locations. But when you're on the arterials, the loop location, because of the stop and go condition, the traffic stops, Q builds up, your equation is not straightforward, going to give you the density for the entire corridor. So that equation works under a stationary condition, means the traffic is consistent over that stretch, which is fine on the expressways, right? That equation will fail when you're close to that congested region for a certain time, but not fail, actually will not give you the good estimate of the density for a larger corridor. You are assuming that flow and speed at one point is homogeneous over the corridor you're talking about. Yeah, but on arterial is not, homogeneity is not there. Near to the intersection is where you have all the Q building up. Upstream of the intersection, you do not have enough Q. In fact, you do not have enough, the density is low, downstream is high. So that equation, the homogeneity is not well, I would say, respected. So you cannot just say Q is equal to K times V to estimate the density for the entire stretch. So that's all this thing is done so that you can have a density estimate or the Q length estimate along the corridor. Now, I'll show you some of the application of this, which we have already shown you in the first lecture when I talked about the macroscopic fundamental diagram. I showed you the diagrams like this, and I said at that time somebody has given you the density. Actually, Cuprite gave us the density by integrating the loops and the Bluetooth for that one. So this whole diagram was generated using Cuprite as the model behind density estimation. And you can see the shape is coming up. I mean, yes, there are errors. It might not be the perfect density. There are errors, but this is the best we can get out of it. That's one of the applications that we discussed. Another application where you can apply this, I mean, this can be input output can be applied anywhere. There's nothing wrong. What you do is amount coming in, amount going out, make a reference point. I keep on adjusting them whenever you have some information. So we have discussed that when the spacings are large, then you are less generally you can estimate this now on the motorways. You want to estimate the travel time. If you have a loop at one location, loop at the other location, you apply a piecewise constant speed based model, assuming whatever speed you are getting from location 1 is constant for the half of the distance with the other loop. You get that one. But as the spacing starts increasing, you will have more and more errors. We have shown that yesterday when I was showing you when I discussed this model. Like for example, in this case, this is a passing motorway. You apply that model. There are instances when the spacings are large and you might have some errors somewhere. And you want to generate this kind of heat map. So one way to do this is when the spacings is large. Let's say you have a very large, maybe 2 kilometers apart loops. And there are on ramps and off ramps in between. So they are middling, source and sink. You can still apply this with certain hours adjustments. For example, if you apply a piecewise constant speed based model from upstream to downstream, you might get a travel time as shown here. But this travel time might have its own errors based on the spacing. So what we said that we can think of a treatment period. That in this period I would like to make some treatment, I would like to adjust my travel time, and I need some hook points in the cumulative plots. So from this loop and that loop, I can get my cumulative plots, but we know that there is a traffic coming in, traffic going out. So I need to adjust that. So I need some hook points. So what hook points you can think of here? Oh, it will generally increase and it will go down. Well, because as the congestion is going to increase, the traffic will go up and go down. When the system is not congested, you will have a free flow travel time. You don't have to worry about anything there. Even if the loops are apart, you are fine. It is only when the system is congested. So that's the place when you have issues. For example, here, this portion of the network system is free flow. Don't worry about it much. This is the place where, or this time period, this one's where you are interested in. So what can be the potential hook points? But I have a loop here, a loop there. From here, that one. No, but I have no information who's entering and exiting. What I only know that from here to there, the travel time profile is like this, based on the piecewise constant speed based model. So I know the travel time for this whole section, a profile like this. So y-axis is travel time, x-axis is time. So at certain time, the travel time is free flow, means very low value free flow. Then travel time starts increasing, and then starts decreasing, goes back to free flow. Yes. So free flow is definitely your hook points, right? Because that's the time you know that the travel time should be close to free flow. You can have additional hook point, which is the peak value. But when the queue extends, the congestion comes, your piecewise constant speed based model is going to give you good results at that time easily, because you are generalizing here and there is going to give you good results, because the whole system is congested. You might have a speed of 20 here, 20 here, or maybe 20 here, 30 there. Average is fine. So I have 3 hook points here. So the first hook point is, I will say, maybe half an hour or sometime before start of congestion. Second hook point is also sometime before, and the peak one. 3 hook points I can easily get. So I draw my cumulative plots as shown here. I say this is the area, this is the time when I want to make some treatment, because I know that this is the time period which is actually this whole time period from here to there, right? I want to do some treatment, and I have 3 hook points, 1, 2 and 3, and I know their travel times at those times, right? At time start with the free flow travel time, time end with the free flow travel time, maybe a time in middle with the congested travel time. We know that we put those 3 hit points, and then we apply cuprite, shifting, vertical scaling, shifting to actually generate the plots there, right? And what we observe that by doing so, you are able to have a 10% improvement in the accuracy and whatever. Like, I mean, these are the values which are values, but the concept I'm trying to tell you. We even try to validate this on a real network. That is a motorway section. You have a Bluetooth here, a Bluetooth there, and a Bluetooth here. It's around 2.75 kilometers from here to there, and 3.42 kilometers for that section. So what we do here is, because you have the Bluetooth based travel time, here the green line represents your hybrid model, the one I just mentioned. The red one is the piecewise constant, and the blue one is the Bluetooth one. You can see they are pretty much close to each other. The Bluetooth is giving, I mean, it is only when the spacings are large. If the spacing was small, I mean, this is 3.42 kilometers. The spacing was, let's say, 500 meters. You don't have to go in all those complexities. Your piecewise is giving you good result. Only when the spacing is large, then you will go for that additional, I would say, adjustments to actually make some more better estimates. This is another, I think, they are, I mean, that's actually one time period, that's another time period. I'm just showing you some of the graphs here.
Which one you refer to, hybrid or the?
Oh, if I have the Bluetooth, I will go with the Bluetooth. I don't have to worry about the hybrid for travel time. If I have the Bluetooth, I will go with the Bluetooth. I will have more confidence in the Bluetooth because that is the actual travel time you're observing. But I'm talking about when you do not have the Bluetooth, you have only the loops, then you can still make a good estimate. It all depends on the use case or the whatever is the steady state requirements are.
Sir, Bluetooth installation is done for the traffic study or for something?
Or for travel time estimation. Yeah, only for travel time. Everywhere in yeah, it is just for travel time.
Sir, when like studies are done, that preferred distance should be less than all. So why this gap?
Um, See this gap. I've shown you earlier that whenever you have the loops can fail.
No, no,
Hmm.
the distance of the Bluetooth.
Or distance of the Bluetooth on the motorways. I mean, they have installed the Bluetooth on the motorways based on whatever logistics they had. On the intersection, it was pretty much easy. Signal intersection, signal controller box is there, electricity is there, plug it there. On the motorways, you have to look at where you have the because you want to minimize the cost. You don't want to bring it as a separate one. So it has number of other logistics. But this, it may not be at all the motorway sections you have it. Still, like the coincidence is quite big. Certain sections, there are a number of them where you don't have the Bluetooth. Then you are relying on some other source.
Basically, what you are saying is we cannot expect all the facilities at all the locations.
Yeah.
So we need to adapt for all the.
Yes.
That's
Yes.
why
That's why you have it. Now, again, in Brisbane you have it, but you might not have it other places. You might have only loops, let's say on the Jaipur Expressway, you might have installed some sensors which are maybe 2 or 3 kilometers apart. Then you might like to apply some other tools or some of the other treatments on that estimates to make it better. And you are able to test it on some other network. I mean, these kind of papers, this kind of work can help the applications in the sites where you do not have the data set.
with wherever both sensors are available, that we validate that techniques will implement it.
And other place, yeah. I mean, if you have both the sensors there, I mean, for this site, I will.
Validation.
Yes, yes, yeah, yeah. So we can, I mean, you can ask, maybe we can have maybe 2 minutes break, stretch yourself. I think it's almost 1 hour before we go to the next one. Any question from the online audience?